Now, let us learn how to plot graph. What we have been doing all this while is sketching graph. Plotting graph eliminates some, if not all, the problems associated with graph sketches. In the course of time, you know about those problems. In the meantime, let me inform you that there are 6 steps recommended to be followed when plotting graph, whether linear or nonlinear graphs. The following steps are recommended for plotting a good graph. Number 1, layout. Number 2, choosing and stating the scale. Number 3, calibration. Number 4, locating tabular values on the axis. Number 5, locating spatial points of intersection. And then number 6, drawing line of best fit. Let us start with the first step, which is layout. Join me as I explain it and apply it. Please listen. What you see on the screen is the graph page. That which I said is an advancement over the Cartesian system. Before we proceed, let us look at some of the important features of this graph page. The characteristics, that is, as you watch the graph page, there are properties or features that are peculiar to it. The first of the features I want to consider is the existence of many horizontal and vertical axes crossing one another. In the simple Cartesian system, you have only one horizontal axis and only one vertical axis. But as you can see, this graph page contains several horizontal axes and several vertical axes crossing one another. This is the first of the features that you have to bear in mind. The next feature I want to consider is that the graph page has suggested and predetermined intervals. Predetermined intervals. What does that mean? It means that already, unlike the simple Cartesian system, it has gaps which have been suggested to be used as intervals. These gaps are suggested from here to here is an interval. From here to here is an interval. From here to here is an interval, all along the vertical axis. Likewise, from here to here is an interval. From here to here is also an interval. And these are along the x-axis, the horizontal axis. The next property is that the graph page contains specified number of unit boxes in one interval. Unit boxes. These small boxes scattered everywhere over the entire graph page are called unit boxes. Here, we notice that every interval has a specified and constant number of unit boxes. If from here to here is one interval, like I said before, let us count how many unit boxes there are in that interval. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different unit boxes in one interval. Do we have 10 unit boxes in every interval? Let's count the next interval from here to here, with view to knowing if the same 10 will be in it. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wonderful. It is therefore assumed that everywhere along the vertical axis, there are 10 unit divisions, 10 unit boxes. Let us count how many unit boxes there are on the x-axis. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The same 10. Let's count the next interval from here to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Also, 10 different unit boxes. It is also important to note that every graph page differs in its own way from other graph pages. It is possible to see a graph page in which an interval contains 5 unit boxes. There are some graph pages that don't have up to 10 unit divisions or unit boxes. Some graph pages have only 5. Let's say, for instance, we count from 1, from this point, 1, 2, 3, 4, 5. Since we have a tick line here that signals the start of that interval, on the 5th one, another tick line is drawn to signal the end of that interval. That means from the start to the end, there are 5 unit boxes. There are even some other graph pages that have up to 20 different boxes in one interval. But of course, as you can see, this one contains 10 unit boxes. An interval that contains 5 unit boxes is called 1 cm interval. An interval that contains 10 unit boxes is called 2 cm interval. That which contains 15 different boxes is called 3 cm interval. An interval that contains 20 unit boxes is called 4 cm interval, and so on and so forth in that manner. Which type are you seeing on the screen? Don't forget, it contains 10 unit boxes, both along the x-axis and along the y-axis. Which type, therefore, is the interval we're seeing on the screen? It is the 2 cm interval. Another important feature of the graph page is that it provides several positions which we could use as the origin. In the simple Cartesian system, we have only one place we can call the origin. But here, we have many crossings of the vertical and horizontal lines. Each place both lines meet provides us the opportunity to use the place as the origin. This point, for instance, can serve as the origin. This point can serve as the origin. Any of these positions where the two lines meet can serve as the origin. But it is suggested that we use a place where two thick lines meet to serve as the origin. That means that we could use here as the origin, we could use here, we could use here. Don't forget that these are mere suggestions. We can go out of the way to use any place where the two lines meet, the vertical line and horizontal line. Wherever they meet can serve as the origin. Now let's look at the advantages of the graph page over the simple Cartesian system. The first advantage we want to consider is that the lines are straight and accurate. Each of these lines is accurate and straight. If we have to use the simple Cartesian system, especially with a freehand sketch, it is possible for us to make a mistake of drawing a line that is not purely horizontal or a line that is not purely vertical. Because we don't want this mistake, we prefer to use this graph page over the simple Cartesian system. Don't forget,
each of these lines is accurate and is straight. The second advantage is that all the intervals are equal. Recall, at the time we are using the Cartesian system, you saw me giving distances between intervals, preferably using dots. But there was an error, or there was a risk. The risk was that it was possible for me to get different distances for different intervals. If we have to get accurate plot of values on a Cartesian system, the intervals must have the same distance. The vertical axis must have each interval equal in distance to other intervals. The same thing is applicable to the x-axis. Therefore, the graph page gives us the opportunity to see or ensure that the gap in each interval, or the distance for each interval, is the same everywhere. Therefore, we conclude that the size of every interval is the same and accurate. Another advantage of the graph page over the Cartesian system is that we can accurately locate values along any axis. Let's see an example. Assuming that this is origin for a particular plot, and according to calibration, here is 2 and here is 4, and in that manner upwards, we can tell exactly if we want to say, for instance, that we are looking for the value of 2.3. We can tell exactly where to get 2.3. Before, we did it by trial and error. When I was discussing with you a simple Cartesian system, it was difficult to trace exactly the position of a particular value needed. Take, for instance, I'm looking for 2.3. If it had been Cartesian system, I would have just used the trial error to get that position. I would just know that 2.3 is somewhere between 2 and 4, but I will not know the exact position. That is a problem. If we plot a graph of real-life situation and we use such conjectures to locate values on the axis, we end up making costly mistakes, even life-threatening mistakes. But because of this graph page, we can locate the exact position of a particular value needed. For instance, if I want to locate from this 2, between these 2 and 4, a position for 2.3, we can do that. I can do it, and the time is coming when I'll discuss with you how to get the exact position of 2.3, for instance, between these 2 and this 4. That means that with this graph page, we can do it accurately. Another advantage of the graph page over the Cartesian system is that any point on the graph page that we so want, we can point there and tell the value on that position or that point. Take, for instance, if I want to know the value of this position, I can tell, since here is 2 and here is 4. If it had been with ordinary Cartesian system, I cannot tell what this place is accurately. Instead, I'll simply use trial and error method. But with the coming of graph page, it became possible to tell the value of a particular physical quantity being plotted on that graph page whenever you point at any position on the graph page. I can tell what this place is. I can tell what this place is. I can tell what this place is. I can tell any place what it corresponds to. That is an advantage over the simple Cartesian system. Before we go into the actual process of plotting the graph, that is plotting values on a table on the graph page, let us look at the steps of plotting the graph. The first one is layout. You will know what it means shortly. The second one is choosing and stating the scale. The third one is calibration of the axis. The fourth one is locating tabular values on the axis. The fifth one is locating the spatial points of intersection. And the sixth one, running the line of best fit. So far, we can say that we have known or been told about 6 different steps that must be taken while plotting the graph. Please be sure that you don't jump these steps. Step 1 must come before step 2, and step 2 must come before step 3, and in that manner on to the last point. Let us see how to use these steps to plot the table that we have at hand. Now let's use this table, this our forgoing table, to learn how to apply each of these 6 steps of plotting graph. Don't forget that the first of the 6 steps is the layout. The layout. Let us start with it. We're going to do a layout for this table, but first, you would like to know, please, what is layout? Simply put, layout is fixing the origin. That means finding out where the origin is supposed to be. It is important to note that the origin for every graph is not the same. That I said earlier that any of the places where the lines cross can serve as the origin does not mean that any place you want can serve as the origin for a peculiar case like this one. Each time we see a peculiar case like this, that is to say, each time we see a table which we want to plot on the graph page, no longer are we free to choose just anywhere as our origin. Our choices become narrow and fewer in number. Why? It is because the values of the independent and dependent variables have directions apart from magnitudes. The signs before numbers tell us the direction. Don't forget that anything minus refers to either left or down. Anything plus refers to either up or right. These are directions. Look at this, for instance. We have -3 here, and it belongs to x. What it means is that this -3 will be found on this part of the arrangement. This -2 also found on the left side. What about these 2 on the right side of this axis? To choose your layout, the step you must follow goes this way. First, draw the conventional Cartesian system with 0 at the center, spanning through all the 4 quadrants as the origin. Then, let it have almost equal distances for the plus y, minus y, plus x, and minus x, as you can see on the screen. That is the first thing you should do. That is, draw it like a cross, the way I'm seeing it there. After drawing it like a cross, the next step is to go back to the table and determine if any of these axes or subaxes will not be necessary in plotting the values on the table. How do we know? Take, for instance, here, I want to check whether both left of x and right of x will be needed in plotting this table. Let me go there. We have negative values of x and positive values of x. Because of that, the layout will include both the left and the right of x. The same thing should be done to y. Y has negative values and also positive values. The negative values of y are minus 19, minus 13, minus 7, and minus 1. All of this will be located below. That is from this 0 downwards. What about the positive values of y? They are the 5 and 11. They will be found on this subaxis. That is from this point upwards. So far, what have you observed? Is there any of these subaxis that is not necessary for plotting this table? No, they are all necessary. But it is important to note that sometimes we have tables that make it possible for us to use only 2 out of these 4 subaxis. If I say 4 subaxis, I mean the plus y, the minus y, the plus x, and minus x. If we count them, they are 4 in number. We call them subaxis. So we have 4 subaxis here. For this table, recall, we're going to use all the 4 subaxis. But there are tables that will make it more convenient to use only some of these 4 subaxis. Take, for instance, if all the values of x are positive and all the values of y are positive, you will not need this side much and this side much. What you now do is that you take more space on the right part of x and more space in the upper region of the y, so that you leave a small space on the left for x and a small space down below the central origin for y, de-emphasizing the application of these subaxis. Sometimes we have tables that force us to use 3 out of these 4 subaxis. Imagine that this x has both positive and negative values, but every value of y is positive. What it means is that we shall need only 1, 2, and 3 to plot. In fact, if we keep on cutting off axes, if we keep on cutting off subaxis from this arrangement or array of subaxis, we end up getting up to 9 different layouts. This is the most conventional. This is the most basic layout. It is from it we get other special layouts. Special layouts are made special by the type of table we're going to plot on it. Therefore, for plotting these values on this table, we're going to use this layout the way it is in this basic form, since we have known that both x and y have both negative and positive values. This is all we have to say about layout. But bear it in mind that we're going to meet several cases in which you will be faced with deciding which of these subaxis will not be emphasized. Having done this, therefore, since this table is what we have at hand, let us draw this cross layout, the basic layout on our graph page. Let us see. What you see on the screen is a suggested layout for this table. Please take note, this table is not a part of this graph. It is pasted here just to make it possible for you to relate constantly with what you are plotting and the values on the table, so that each time we locate any value on the graph page, we can make reference to that value on the table. Therefore, this table is not part of the plotting, but is here for easy reference. Again, look at this layout. This is the origin. Why? Of all the places I could have used as my origin, why this point? Anyway, look at this table again. Though we have chosen the cross layout, that is the basic layout, it is very clear that the space I left for minus x is more than the space I left for the positive x. Why? If you watch here, you have that the magnitude of minus 3 is more than that of 2. We are not talking about which number is less and which number is more. We are looking at a number whose magnitude is higher, irrespective of direction. With that in mind, we conclude that minus 3 is higher than 2, only in magnitude. Therefore, since minus 3, we need more space than these two. I left more space for the left side of this x than this side of this x. Let us look at the y. This is the y-axis. I also left more space down here than up here. Why? If we look at minus 19, which is the highest in magnitude down this side, you compare it with 11, which is the highest in magnitude for the values that will be up here. You see that 19 is more than 11. That is, if sign is not taken into consideration, 19 is more than 11. In fact, in plotting values on graph page this way, we do not look at the mathematical relationship as to which one is higher or smaller. We know that mathematically, based on accounting principles, that 11 is way more than minus 19. The reason is that 11 means plus 11, and it means having 11. And minus 19 means owing 19. And we know that somebody that has 11 is richer than somebody that is owing somebody 19 and has nothing. Therefore, even this minus 1 is more than minus 19, because somebody who is owing 1 is richer than somebody who is owing 19. That is not what is going to lead us in our action, in our activity of plotting values on this graph page. Instead, we look at the magnitude, whether owing or having, which one is higher in magnitude. That is all that matters in plotting values on the graph page, not which one is higher in the real sense. Because of that, since 19 is more than this 11 and it is minus, we left more space down here than up here. Therefore, eventually, the entire layout is still cross layout, but not symmetrically arranged, in the sense that all sub-axes will not be equal, except on the table we see that it is possible to do so because the values are either equal or nearly equal. And now, checkpoint, it says, sketch a layout for each of the following tables. There are 4 tables: table I, II, and IV. Each of these tables has its own feature. I understand that some might be confused as to what they're supposed to do. Please, even if you go ahead to plot, that will not be a crime. But the most important thing is that you sketch a layout. Choose an origin for each of them. That is instruction.